Okay, so now we are broadcasting live on Twitch. Okay, so my name is Jason Biggs. I am a developer for Wolfram Research. I've worked in Wolfram Alpha and then more recently in Mathematica, developing some chemistry functions that we're introducing in version 12. Um, I'll talk a little bit about what all offerings we've had for the chemistry community up until now. But we'll start. I'll just give a brief overview here of the marketing page, which we'll be using as a guide. Um, Starting in version 12, we're introducing a whole new host of functions centered around the molecule, which is a symbolic representation of a real world molecule. Um, it's modeled on the graph that has been in the Wolfram language for many versions now, and it's a mature um, functionality. And so now we're building on that, and we can give you the molecule, which is at its base a chemical graph, some atoms and bonds. So we also introduce visualization functions and substructure searching, some geometry optimization, coordinate manipulation, topological descriptor computing. A lot of these things is a whole host of new functionality that comes in version 12. So here we see the examples are all divided up into 6 rows. So we're going to have uh, to to not get lost here if we want to get through all of these. And we also see this is the list of the new functions or new or updated functions for molecule. We've got at its base, it's filled with atoms and bonds. It's got a list thereof. It's got molecules, molecule patterns, molecule graph, all of these things. We've got a couple of guides. We gave a talk recently at the tech conference, and so you could also watch that and see how the functionality changed between last October and when we released. Yeah, so I think first I'll take a brief aside here and talk about what has been in the Wolfram language so far. So I've prepared this section. So since version 6, we've provided access to thousands of curated chemical entities via chemical data. So right now, it's got, so I'm going to say that again, curated data for over 40,000 molecules, meaning that everything that we have in the knowledge base came from some definitive source, such as NIST or PubChem. And if we look at the entities in chemical data, you can preload this cache so that it doesn't do this during a live stream, but I did not evaluate this particular cell. And so what it's doing right now is downloading the list of all 44,000 entities that we have in chemical data, and it's going to display them for you. So in that, you've got entities like isononyl peroxide, and we've got data in there. So say your van der Waals constant or your melting point. We've got a structure diagram that we've pre-computed and stored there. And you can access that via either chemical data or entity value, which are have both been in the language for some time now. And yeah, there we go. So it takes a little while to download all the entities. But so that's what we've had so far, and that's what we've had as far as curated data goes. And so now, what we want to bring is the molecule. So when we create a molecule, when I say mol equals molecule water, so what this is doing is it's creating the data structure on the fly as you ask for it. And format that. So it's a list of atoms and a list of bonds. So there are 2 bonds and 3 atoms, two hydrogens and 1 oxygen. You can also, you can access that via its atom list and its bond list. You can ask for properties of them all. So here, we're going to ask for its molecular mass and for the point group. And here the point group display, because we wanted to show up with a nice subscript. And so So it's comes back as a quantity, telling you that each molecule of the, in this case, water, weighs 18.0515 atomic mass units, and it has C2V symmetry. And again, these I'll try not to belabor this point too much, but these are computed on the fly. Let's see. Yeah, so there's a question, any drug discovery functionality? Not at the moment. I mean, so we were kind of laying the groundwork for that, right? The data structures that you would need to do that. I imagine, yeah, I imagine you could use the tools herein to do that, but there are no built-in functions to do that. Right. So you create your molecule, you query it for properties, and then you can change said molecule. You could take the molecule, that water that you just made, and set the mass number on atoms 2 and 3 to 2. And in that way, you make heavy water. So that's the first introduction here. Now, once you've created a molecule, you want to visualize it. And so for that, we have molecule plot and molecule plot 3D. So you start out, you notice that when you create a molecule, it displays visually in front of you. It's got a summary box, which you see in a lot of built-in functions, and it shows you the plot, a small sketch of what it's going to look like. And you'll notice that when you hover over any of the 2D diagrams, it gives you the atom index. So here you see I'm hovering over atom 5, atom 2, atom 3, 1. And so that ends up being very useful for functions that require you to know the index for various atoms. Okay, so here we take a molecule 1R, 2R, 2-amino, 1,4-nitrophenyl propane 1,3-diol, and we can look at the various different plot themes available. So I can just do a molecule plot of M, and it looks like this. It shows, right away you can see that it shows, has different colors for different atoms. Nitrogen show up in blue by default, oxygen in red. We've got, we show stereochemistry by default. So this indicates that if these two bonds, if the lines representing these two bonds are in the plane of the notebook, then this oxygen atom, the bond between this carbon and this oxygen, is coming out of the notebook. Likewise with this carbon-carbon bond. So that is displayed by default. If you want to, so there's a whole host of options here. If you want to change the colors, you could use the color rules option. So we could say oxygen should be green and carbon should be blue. And that way we could, you can restyle the default options for the plot. We could just make everything blue except for oxygen, which is green. So we could also apply plot themes. Plot themes can help us control whether or not we show all hydrogen atoms or whether we have them elided, as we say. So here you don't show all the hydrogen atoms. They're there. They're implicitly there, we say. You can choose whether to show this aromatic ring as delocalized single and double bonds, or you could show it as a circle like this, representing the delocalization of electrons around that ring. Let's see. And likewise, again, for the 3D version, you can choose whether to show bonds, whether to show the atoms. If you want to show space filling, imagining each atom to be a sphere. And then likewise, the next thing you'll want to do when you visualize these is to highlight something. So here what we do is we plot M, and we highlight atom 9, and we plot, highlight the bond between atoms 2 and 5. So what that shows is this is atom 9, which I've chosen to highlight, and then this is the bond between 2 and 5. If we wanted to, we could do the same thing, but we can specify a color, style. I always choose green just because it stands out. So there, so that's how you would apply color to a various styling highlight. And most everything should work exactly in 3D the same way. Okay. And so let's see. So we have another question. Any function for the field of physical chemistry, like chemical thermodynamics? Let's see. So we've had thermodynamic data for quite some time. This was introduced in version 10, and so there's a fair amount of computation available in here. And this is all. A lot of this accesses data directly from NIST that is provided in the build using a library provided by NIST, RefProp. And so you're this allows you to do a lot of computation. Yeah, so it's not just static data. It's time. It's a temperature, pressure dependent data and whatnot. If there's any other types of physical chemistry applications that you would be interested in having for the Wolfram language, do not hesitate to file a feedback and tell us what kind of functionality you want. So I've spent a lot of time on chemistry and for version 12 and going forward to version 12.1 and beyond. And so any feedback that you have, please don't hesitate to let us know. Just go to the help menu, give feedback, and here just please tell us how you feel about the product and what you want for the future. Right. Okay. So that was visualizing the molecules. So now we want to talk about molecule patterns. So let's close this up and start a new section here. So in order to highlight, so molecule patterns are useful when you want to highlight a particular pattern inside a molecule. You want to search for inside a group of molecules for molecules containing a particular functional group or a particular chemical species. So that's where patterns come in. So here, so you can have patterns that represent individual atoms, patterns that represent individual bonds, or patterns for arbitrary substructures. So here we have a list of 3 patterns that represent particular 3 atoms. So this first one matches any oxygen atom. This matches any cation, or any atom with a positive formal charge, and this matches any ring atom. And so now we can So what I did here first was I created an association where I give a label on as the key and the molecule pattern as the value. And so I give that as the second argument to molecule plot. First is a molecule, trinitotoluene. So when I evaluate this, it turns into the molecule here. And then the highlight rules, this is the association. And so it'll take the keys to form the legend. And you can see right away that it picks out these nitrogens as a cation. It picks out that these are ring atoms and that these are oxygens. If I wanted to, I could have made a different pattern for oxygens that was only for neutral atoms. So here what I do, this is a pattern for an oxygen atom with a formal charge of 0. And so it doesn't match these 3 anions. Right. And so likewise, we can do a pattern. We can have patterns for bonds. So in this case, we've got a pattern bond NN matches any nitrogen-nitrogen bond. We've got here we've got a bond between a chlorine, a fluorine, a bromine, an iodine, and anything else. So that's a halogen bond. Or we can be a little bit more complicated and have a polar bond. So this is a bond between two atoms. Let me expand that to make it a little more obvious what's happening here. So this is a bond, and the first member of that bond is an atom with a partial charge greater than 0.2, and then the other member is an atom with a partial charge of lower than minus 0.2. So that's what you might call arbitrarily say that this represents a polar bond. And so then these are found inside the molecule very easily. And so this is represented as the only polar bond in the molecule. Let's see, I have to mute and sneeze. Okay, no, that didn't happen. All right, maybe next time. Let's move on. So that's how you would represent a bond or an atom in a pattern. And then more important, or just as important, but more complicated, is an arbitrary substructure. So what do we have here? So this is a molecule pattern where it has two arguments. The first is a list of atoms, the second is a list of bonds, just like the molecule. So here, in this molecule pattern, you've got a carbon, you've got an oxygen, and then you have an oxygen that is bound to at least only two heavy atoms. So this won't correspond to a negatively charged oxygen that only has one atom bound to it, or and it also wouldn't match on a hydroxyl group. So this is a pattern for a carbonic ester. So let's look at it in 2D just for just initially. So it matches. So this is where it matches the carbonic ester pattern, and in 3D we have it here. And so it's near instantaneous when it finds these patterns and highlights them. And so that's one thing that's really great about the substructure searching. It's very fast. So that takes us to molecule pattern. Now we have substructure matching. And so this is interesting. So if, say, you have a list of molecules and you have a particular pattern and you want to select the molecules that meet that pattern. So here we'll take the chemical class of ketones and create a molecule from it. And so essentially this is querying the knowledge base to get a list of ketones and then creating molecules from them. And there ends up being about 900 and something chemical entities in the entity class ketones. And so we create a list of molecules from them, and then we define a pattern here matching an ether. So in this case, we're using a SMARTS pattern. This is like regular expression, but for molecule patterns. And so if you understand SMARTS patterns, this is an organic carbon atom, and this is an oxygen, again with a heavy atom coordination number of 2. So this is essentially the same. So this atom O with heavy atom coordination number 2 in a SMARTS pattern would be represented as OX2. Likewise, this lowercase c is an aromatic carbon, so it would be an atom carbon with aromatic atom Q goes to true. So it's a more verbose language, but it's some people will find it easier to read and understand this syntax than this syntax, but the Wolfram language supports both fully. Right, so here we create this molecule pattern for ketones for an ether, and we select only those those ketones that also represent a diaryl ether. I made another example here. I thought this was fairly neat. I have it prepared off screen. Bring it here. So, right. So hemiacetal as a compound that results from addition of an alcohol to an aldehyde or ketone, respectively. So we can so first, let's create a list of molecules, and this is a list of 2,000 smile strings. This is kind of a show-off, just to show how fast it is to create 2,000 molecules in about 2 seconds. Here we have this pattern representing the hemiacetal functional group. And now we select those molecules in the list that we just created containing the hemiacetal pattern. And let's look at the timing. It's very fast. We see that there were 5 matches. We can look at them, and we can even plot them and highlight the acetyl functional group. Let's see. Okay, so that takes care of the first row here. Now we've got the second row is all about constructing molecules, how you might construct them. So this is one of the things that really got this whole project started, was we can have chemical entities, and we have a chemical entity representing 1,3-dichlorobenzene, right? And we can find this guy by, so we can create a molecule from that, and then we can find if we have that in our knowledge base. And so we do. We have one canonical representation of 1,3-dichlorobenzene. And it has a name property, right? It has, and that's its canonical name in the knowledge base. But really, there are many different ways to write that. You could write 1,3-dichlorobenzene, 2,4-dichlorobenzene, 4-chloro, 6-chlorobenzene, meta-dichlorobenzene. There are probably more ways to write this out. And it, for a large knowledge base, storing all of these names as keys so that pointing to this entity becomes it becomes really hard to do, and it doesn't scale well to a huge list. And so what we do now is we use the opsin library to parse this directly to a SMILES string, which is a more direct encoding of the chemical graph. So we can do, we have this, it's in our function repository. So we have resource function name to SMILES of this. And so this is the canonical SMILES string representation of 1,3-dichlorobenzene. And so when we create a molecule out of all these 1,3-dichlorobenzene, 2,4, meta, they all end up producing the same molecule. And we can prove that by asking, are they equivalent molecules, molecule equivalent Q? Yes, they are. And so with that said, another little show off that I always enjoy is how fast this is. So you have this list of names, and you can easily evaluate them and instantly traverse the chemical name, turn 4,5-dihydroxy into these nodes on the graph of hydroxy at the 4 and the 5 points, or 4 and 5 locants, as you would say. You create the chemical graph from the chemical name, and then from that we create the molecule. And it even works for this guy. So yeah, I'm always impressed by the opsin chemical name parser and how that works, and how well it works. Our next example talks about the SMILES string, which if you're going to encode molecules as a graph type data structure. The SMILE string is it's going to be one of the intermediaries you use. So it's a string encoding of the chemical graph, as I've said a couple of times here. So the basic building block of it is the atom. So here, this is a SMILE string for just a disconnected xenon atom. Molecule plot 3D of that should be relatively boring. Yes. Let's see, and then if the chemical bond is represented by a single bond is implicitly there with two atoms with nothing between them. So this is hydrogen. We could modify that. If we just put a dot between the two hydrogens, then that means there is no bond. And so that's two disconnected hydrogen atoms with no bond. And so if we look at the atom list, we'll see that that these have unpaired electrons. So if you don't have the unpaired electrons, then the molecule will attempt to fill in any valences. So if I just create a molecule with just an oxygen, it turns into water because oxygen by itself wants it wants to have two bonds formed. So if I wanted to explicitly represent just an atom by itself, I would have to say atom unpaired electron count goes to 2. So that is an oxygen with no bonds, and it's just got two unpaired electrons. So another way to write that would be to just write molecule O. Okay, so that's the basics of the SMILE string. We can do a lot more. So C represents methane. You could make a chain of carbon and nitrogen and sulfur atoms. You can represent different types of bonds. A double bond is an equal sign. A triple bond is the pound sign. You can represent a ring closure. So this is pretty neat. So this represents, let's see what its name is, right? 2-entity 135 hexatriene, or by for putting this 1 here, it represents a ring closure. So that says that this atom, this carbon is bonded to this carbon. And so in that way, you have the 135 hexatriene or benzene. And they're related to each other just by a bond, a ring closing bond. Okay, which brings us to modifying molecules. So if those two are related to each other just by a ring closure bond, then one ought to be able to just close that bond. So let's do, well, let's follow the example. So here we start with N-hexane, which is just C6H14, just a straight chain of 6 carbon atoms, and we add a bond between atoms 1 and 6, and we make it a single bond, and that forms cyclohexane. You can add a new atom, a new oxygen atom, double bonded to atom 1, and that becomes cyclohexanone. You can set the formal charge on that oxygen to -1, which would then automatically convert it into a, let's see, it would convert the double bond on the atom between the oxygen and the carbon into a single bond. If you didn't want that behavior, then you would set valence error handling goes to false. And so you do get a message telling you that it has an invalid valence for the oxygen atom, but you still have a valid molecule that you can work with. Likewise, you can replace an atom. Here you start with benzene and you replace atom 1 with a nitrogen. So this example is fairly neat. You can do more complicated replacements. Rather than just replacing a single atom, you can put in a whole substructure. So in this one, we start off with cyclopentane. You look at molecule plot 3D, it's generated coordinates. Now we say replace substructure, but we make every hydrogen atom a benzene. So let's visualize that better in the notebook, right? So that's M, and now we replace every hydrogen with a benzene. And so what is that? So here at the center is our original cyclopentane, and now each one has two benzene rings on it, two phenyl rings. Probably a very, very highly unlikely molecule. I can't imagine the adverse conditions under which you would get this to form, but I was never a synthetic chemist, so that's yeah. But in the computer, I can be a synthetic. Everyone can be a synthetic chemist. Right. So then we can go a little farther. So that was a simple substructure replacement. We can also now go and replace this central ring inside there with a 10-member ring. So here we've got a 5-membered ring, but now we want to replace it with a 10-membered ring. So we do molecule modify. We tell it we want to replace a substructure. The thing that we want to replace is this pattern that is it's a smart string representing cyclopentane, and we want to replace it with cyclodecane. So replace the central 5-membered ring with a 10-membered ring. But this is to do this kind of pattern replacement, you need to specify the attachment points. So you're replacing a 5-membered ring with a 10-membered ring, and so you have to say you have to give a mapping between the atom indices in the pattern and in the replacement. And molecule plot 3D. Again, that seems like a very Herculean synthetic task to go from to replace the central cyclopentane with a cyclodecane, but rather easy from the desktop. All right, so that is the first 2 rows. Now the third row talks about 3D coordinates, molecule geometry. So I'm typing to someone here. What is the time limit? Okay, so let's look at the coordinates. So we create a molecule. We create molecule of adenosine. We can just when we do that, this is fairly neat, and I don't want to gloss over the fact. So when we create that, it has no coordinates. We started just with the name, and then we created a chemical graph. And if we look at the input form of this, there are no coordinates in that. It's got a list of atoms, it's got bonds, and it's got some information about the stereochemistry, but there are no coordinates. So when you ask for the 3D coordinates, when we ask atom coordinates, and it generates this array here. We can look at the normal form of that. It's nice to hide everything up in the summary box in the notebook. But if we look at that, it's a list of 3D coordinates, each with a unit in angstroms. That was generated on the fly using a distance geometry method that's informed by, there's a lot of, let's see. So it uses distance geometry to come up with initial embedding. And then it cleans up that embedding by using some experimental torsion angle preferences that were gleaned from the Cambridge crystallographic database. And then after that, we apply a small optimization using the MMFF force field. So, and that all happens in between the time when I click this and this. Those coordinates are generated in that method. If you wanted to, you could generate then 100 different conformations with random, each with random random coordinates. Yeah. So if we wanted to, you could You create your molecule of adenosine, you create 100 different coordinate conformers of it, and then you plot them together. You could look at the distribution of the energy using the MMFF force field. You could then take those conformers and optimize the geometry using the MMFF. And that universally lowers all of the energies, and it makes it a much tighter spread. And so then you could take from those 100, take the one that has the lowest energy. So another neat example, looking at the internal coordinates, bond lengths, bond angles, torsion angles. So here we create maltose, a simple, I believe we call that a disaccharide, right? Somebody can correct me if I'm wrong there. So we create this disaccharide, and we ask what are its bond lengths, right? So let's go ahead and do that. We have our maltose, and now we want its bond lengths. And again, right there, in a very short period of time, it generated 3D coordinates and returns to you the bond lengths. And you can ask for the mean. What is the mean bond lengths in maltose? And it turns out to be 1.274 angstroms. And this, it should be noted, this means this is the mean bond length of this model of maltose. This doesn't mean we didn't make any call to a crystal structure database. We didn't make any call to the knowledge base. So this is purely generated. So in this 3D model that we've created, the average bond length is 1.2 angstroms. You could, if you wanted, look at the bond lengths by type. So here, the way we would do this is we would first find the bond list of maltose and ask for every type of bond, give us the atomic symbols involved and the bond length. And that gives us this big list. So we have for every bond, there was an oxygen-carbon bond that was 1.4 angstroms, CO of 1.4 angstroms, CH, OH. But you'll notice that they come in different orders because the bonds aren't ordered by themselves. So now what we do is we group them, group by that bond list. I'll just put a percent here because we're doing it interactively. Group by percent, sort of the first element, so make it so that OC and CO are the same, and then goes to last, which is the bond length. And so if we look at that, it gives us an association. So the carbon-oxygen bonds, and here's the list of the carbon-oxygen bond lengths: carbon-carbon, oxygen-hydrogen, carbon-hydrogen. Now we can map mean around, and this gives us a more meaningful data point, because it's not exactly meaningful that the mean bond length is 1.27 angstroms, because that hides the fact that the oxygen and hydrogen bonds were much shorter than the carbon-oxygen bonds, or the carbon-carbon bonds. Right, and so to generate a list of bond angles, it's a little bit more complicated. So here we took advantage of the function bond list to get all of the bonds and their properties. There is no such function for angles, so we resort to creating a pattern for an angle. So here I have an angle pattern that represents just 3 atoms connected by any kind of bonds. So this is a Smarts pattern. You could also make that as molecule pattern underscore bond 1, 2. Two, 3. But like with regular expressions, those people who know how to use them will often use them because it's just shorter to type. So here, this angle pattern is what I'll use for any type of angle in the molecule. So we use fine molecule substructure to find all of the angles in maltose. And I'll apply short so that we don't display all of them here in the notebook. But right, so atom 1, 2, 3, 1, 2, 25, 1, 2, and 26. That's those three represent a bond angle. There's a bond between atoms 1 and 2, a bond between 2 and 26. And then by going through similar set procedure as with the bond lengths, you find all the values for the bond angles, you group them, and then you do a box Whisker chart here. And it can show you that the spread, that the COC bonds in maltose have a much smaller spread and a higher value than the CCO bonds, for example. I think this is also a fairly neat example. So start with and this was so this example I got from looking at the literature, right? So these types of plots definitely show up in cheminformatics literature, and so it's really easy to do it here in Wolfram language. So start with 3 examples of molecules with vastly different shapes. So buta-1,3-diene, benzene, and adamantane. These represent the rod, the disc, and the sphere. It's about as spherical as you might get without resorting to Buckminster fullerene or something. So you can look at their principal moments of inertia, and this tells you what type of rotor they are, right? So for our rod, for our linear molecule, what is it? IA is much smaller than IB and C, and these two are equal to each other. For the disk, the first two, the two smaller moments of inertia are equal to each other. And then for the sphere, all 3 of the moments of inertia are equal to each other. Some numerical, some numerical difference there. And so there's a common property that people will look at called the normalized principal moment ratio. So what we do here is we take the smaller 2 moments of inertia and divide them by the largest moment. And so that ends up giving you 2D coordinates. It's a form of a dimension reduction, right? So if we look at that for the rod, disc, and sphere, they form the corners of a triangle. And any set of molecules would be, any other molecule would then fit within that triangle. So it can be fairly interesting to take a list of molecules here from 300 different SMILE strings and to plot where they show up in the this ternary diagram. And you can, using the code here, you can put a tooltip on each of those points to represent the 3D plot. And so you'll see the more spherical out by the adamantane, or the more flat disc down here by benzene. Yep, that was a neat little example. This is an example similar that you might find in a general chemistry textbook, right? So here we'll use the MMFF force field. We'll vary the torsion angle in ethane or in butane, and plot the resulting energy surface. So what we do, so first you start with your butane. You can look and visualize the torsion angle. Let's see, let's go ahead and create that so that we can interact with it in 3D. I'll show this code. Right, so we have this helper function here, plane from 3 atoms. So it gets the coordinates from any 3 atoms and creates an infinite plane from them. And so we show the molecule plot 3D of butane along with a plane containing atoms 1, 2, and 3 and atoms 2, 3, and 4. And so the torsion angle, so if we were to look at butane, let's look at its molecule value, butane. torsion angle 1, 2, 3, 4. So it's 65 degrees. And so that is the angle between these two planes, the plane containing atoms 1, 2, and 3, and the plane containing atoms 2, 3, and 4. So quite easily you can do a relaxed potential energy scan. So what this does is we, so let's see, better show. So we start with the carbon indices 1, 2, 3, and 4, and now we do a table where we change the torsion angle for those to be between minus 180 and 180. And at each step, we perform a force field optimization of all the other degrees of freedom in the molecule. So you evaluate that, and you can get this plot. So this shows you the relative energy, or the absolute energy in the MMFF scale as a function of the torsion angle. Now, normally you would be interested in running this type of scan using a higher level of theory besides a force field. You might want to use some Hartree-Fock or a post-Hartree-Fock or a DFT method. And so that's one of the areas we're definitely interested in looking at. Let's see. Yeah. So this, and then you can look at the highest and lowest energy conformations. So this would be the highest energy. It tells you you get the highest energy by when you put these carbon atoms closest to each other, and then you've got the repulsion between the electron clouds on these hydrogens is at its maximum for that value of the torsion angle. So what does that get us to? Stereochemistry. So this is something that has been pretty much absent from chemical data, and so it's very important in the new molecule that it fully respect stereochemistry. And so right now we support chirality and double bond stereochemistry. Other types of stereochemistry that you might find in inorganic substances is definitely something that we've talked about adding for future versions. Okay, so with 10 minutes left, I should go through this rather quickly. So if we start here with a molecule dithiothreatol, and we ask for its possible stereocenters, that gives back a list of 2 atoms, and it tells us that these 2 atoms are carbon, or are tetrahedral in geometry, and they have 4 unique substituents on each. Each of these has 4 unique substituents, and so their arrangement in 3 dimensions is there are 2 different ways that it could be. I wasn't prepared with a full definition of stereochemistry here, but we can So if you're interested in this, then you probably know about stereochemistry, but let's see. So we created this molecule, and then we look at its stereochemistry. It tells us that atoms 2 and 5 are tetrahedral centers, and the order in which it lists the ligands here that are attached to them determines, along with the direction, specifies the 3D geometry around those chiral centers. You can create an enantiomer by doing a reflection transform. So that's fairly neat. It goes from counterclockwise to clockwise. And then you can look at these and see that these are non-superimposable mirror images of each other. Here we go. We can enumerate the different stereoisomers. So here, if we look at glucose, you can see that it has 4 different stereocenters. Atoms 3, 5, 7, and 9 have stereochemistry. Our chiral centers are tetrahedral in geometry and with 4 different substituents. So if you were to look at the chirality for those centers, you see that D-glucose is RSRR. But if you want to, you could easily use molecule modify to generate the RRRR enantiomer. And you see that that basically that turned this carbon-oxygen bond from being out of the plane of the notebook to into the plane of the notebook. But other than that, they are the same. And so it can be, with a very simple amount of code, you can generate all, is that 16? All 16 stereoisomers of glucose. You can ask about the point group symmetry. And again, in general, this is going to depend on the coordinates for the molecule. So for this case, you can create an ethane molecule and ask for its point group. And we get a D3D symmetry. You can look for all the different symmetry elements for it. We can see that it's got C3 axes, C2, and sigma planes. We could then look at the symmetry planes, right? So let's go ahead and look at the symmetry elements involved in this ethane. So it's got a rotation, it's got various rotation axes, right? And it's got symmetry planes. So then you can take all of those symmetry planes and combine them in a molecule plot. Which I think that this would have good applications, not just in everyday use, but also in education. Okay, so we're nearing the end. We will need to hurry. Yeah. So cyclohexane. This is a pretty neat example. So we've got a cloud object here that's an SD file that represent 6 different conformations of cyclohexane, which have been widely studied in the literature. And so they have these names: the planar, the chair form, the boat form, and then you've got various intermediaries between them: the half boat, the half chair, even the twist boat. So you import them via an SD file. So here we're using cloud import so that users can have access to this SD file. And that, let's just look at that briefly. What is the result of this cloud import? So it would be the same thing that you would get if you just imported an SD file, which is a list of molecules. And then, yeah. So you can look at you can ask them for their point group. You could take that point group and pass it to finite group data to find out about the order of the group. You could query for the energy for these different conformers. Again, using the MMFF force field, which is the only currently implemented force field. You can create a graph here showing the descent of symmetry from the highest to the lowest symmetry species. Right. And then I think that we will just fly through these very quickly. So as we said, molecule is not necessarily just built on graph, but it heavily uses the graph, the Wolfram language graph. And so you can have direct access to that graph by using the molecule graph. And so if we create a molecule here and we ask for its graph, we get this. And so what does that look like if you were to form that? And so it's a graph with vertices and edges and then properties. So this is enough to represent the molecule. So you can then create a molecule out of the graph. Yeah, you can. So you can use that. having access to the underlying graph allows you to use all the built-in graph algorithms in Mathematica, finding cycles. You can find partitions, find graph communities. You can find the longest path in a molecule by using the find shortest path. You can then visualize that path. And we're going to skip generating all the isomers of decane, although it's a fairly neat example, and just end on this where we have a top-level Wolfram language implementation of the atom pair fingerprint. And so this describes what is an atom pair fingerprint. It's any two atoms along with the path in between them. It shows how you might make an atom pair's function for a molecule, which would return the list of the atom pairs, and that shows we have a function to generate the distance between two atom pairs, and then we use that to do similarity searching. So we start with a target molecule, diazepam, and then we take a list of central nervous system agents that were downloaded from PubChem, and we order them based on the similarity to diazepam. And this is functionality that is that we're working hard on for version 12.1, is similarity searching and topological fingerprints. Let's see, I just want to grab Alan gave an idea about doing using the bond length statistics per atom pair. I don't fully understand your comment, Alan, but if you email that or put that in the one of the various chats available, I would be interested in seeing that. Interesting. So an idea to have a metadata for atoms. I'm not opposed to that. We just haven't had a use for it. And then so point group display, finding the point group, approximate point group, having a tolerance option. Yes, it's not, I haven't fully got this the design fleshed out, but you would do molecule property. So here you would say you want the point group display tolerance goes to 0.1, I believe. Yeah. So so there is an idea of a tolerance when looking for a point group, but that's something that needs a flesh out of the design. Yeah. So that is the new in version 12 molecule functionality, or a very fast introduction to it. I hope. Yeah, I hope that anybody has any suggestions or comments, don't hesitate to send feedback. Thank you.